soon enough, so we can get started without them. So I think the point at the beginning today, the first half, is maybe just to rehash the last lecture from yesterday, which was what Dragan talked about, and then make some qualitative examination of these differential equations satisfied by matrix coefficients, and then finish with an actual statement. So let's just recall where we are, because it's easy to get lost. I mean, some of you know this very well, but others it's easy to get lost. So we've defined this category of this category of GK modules. And we're interested in classifying them. Now, let's just remind ourselves why this is an interesting problem, and not just an exercise, say, in algebra or something like that. Well, because a source of GK modules is, say, irreducible unitary representations, irreducible representations of G that act continuously and in a norm-preserving way on a Hilbert space. And that's an interesting problem, classifying all such irreducible unitary representations. So we have a source of these Harishchandra modules that come from unitary representations. The unitary structure on irreducible unitary representations translates into some sort of unitary structure on GK modules. The algebraic notion of equivalence of GK modules, of unitary GK modules, corresponds exactly to the global notion of equivalence of unitary GK modules, or unitary representations of G, irreducible unitary representations of G. So understanding the irreducible unitary objects in this category corresponds exactly to understanding all irreducible unitary representations, which is an interesting problem from the point of view of harmonic analysis, okay? So, but of course there are other irreducible representations in here that may not be unitarizable. We've mentioned that they come from global representations. They all arise as the Harishchandra module, some say Banach representation, continuous representation of G on a Banach space, but some of them may not be unitary. Okay, so that's where we are. That's why that's why we're interested in this. This is not an empty exercise in algebra, classifying these algebraic structures. For instance, if we classify them, we classify a set that contains, by this correspondence I just mentioned, all irreducible unitary representations. So the crude starting point in the classification, well, as I said the last time I talked 2 days ago, if you have these are representations of G, those are modules for the universal enveloping algebra. So a crude starting point is to restrict those modules to the center of the enveloping algebra. And we have this version of Schur's lemma, is that if V is irreducible GK module, and Z is in the center, then Z acting on any vector V is some scalar that only depends on V for some chi V, which maps the center into Z cross. This just says that an element of Z acts, i.e., this just is saying that the action of Z is an endomorphism of V that commutes with the action of the enveloping algebra. So we have a version of Schur's lemma that says anything that commutes with the action of the enveloping algebra is actually a scalar, and that's just the scalar I've written here. Okay, question?
So if you say Z of G, you mean the center of it?
Yeah, so that's the notation. I think maybe Dragan used the notation yesterday, Z of G, but I start writing this starts looking like G, and that starts looking like Z, and it gets confusing. So, okay, so another way to say this is that, and this is the way Dragan was basically saying it yesterday, another version is that, oh yeah, sorry. It's Z. Sorry. So another version of this is that this ideal of codimension 1, Z minus chi V of Z, which is an ideal in the center, annihilates V. So each of these elements, right, take an element of the center and subtract off the scalar by which it acts, of course kill every vector in V, so this is just a trivial reformulation. But that was kind of the way Dragon was sort of saying it yesterday. Okay, so in SL2, of course, the center of the enveloping algebra turns out to be generated by the Casimir. So chi v is determined, well, by just this one scalar, chi v of omega. Okay. All right. Okay, so I mentioned, so let me just, some of you are wanting to think more generally and not just in SL2. So let me just mention a general fact, which we'll probably sketch next week. I don't know how much we'll prove of it, but for arbitrary G and K, not just for arbitrary pairs G and K, not just the ones coming from SL2, we can take a look at the set of V, which are irreducible GK module. Well, let me write it this way. So we have this map from irreducible GK modules to these scalars by which the center acts on them. V goes to this scalar. And the general fact is that the fiber over a fixed chi is finite. So I mentioned that. We had seen that. We've seen this for SL2. I wrote down all irreducible GK modules. There was a parameter lambda, and omega in I'll say my classification, which was kind of muddled. Omega acted by lambda squared over 4 for a ridiculous reason, and I'm going to change this number soon. But it acted by, and there are only finitely, well, at most four V with this lambda label. So if I fixed lambda with lambda label, that's what we saw. So if I fix lambda, that of course in my classification scheme in the list, I had this infinite list, but I fixed lambda, there was at most 4. Those at most 4 representation with the lambda label were exactly the ones by which this Casimir acted by lambda squared over 4. So we see that the fiber of this map for SL2 has at most 4 elements in the fiber. Okay, so we've seen that, but it's a general fact, which we'll deduce from character theoretic considerations, or one can deduce from character theoretic considerations in general. There's no hope of drawing those diagrams for general G, and there's no hope of proving this general fact by enumerating all irreducible representations. So you have to do something more sophisticated. Yes?
What did you write there? The most for...
There's at most 4 V with lambda label.
Thank you very much.
Okay. No. Well, omega always acted by this positive number. I see what you're saying. So there were some equivalences on my list. If I have, I had some p minus lambda, and then, well, maybe I have to, I'll never get this shift right. Plus or minus 1 was actually the same as p lambda. Well, if you make the right choice, if you make one choice here, there's a unique choice here. So there are indeed some equivalences on that list. But but that's a good point. I didn't mention those equivalences carefully. Okay, so, all right, so we want to get inside this, if our goal is to classify, we want to get inside this finite fiber and separate these points. So that's if we're interested in classifying these things. So that's what we're going to do. So how to separate or distinguish, but maybe that's a better way to say it. Harshadra modules with the same infinitesimal character. So, so this map is called the infinitesimal character map. I think I mentioned that. Okay, and so, well, what we're going to do is we're going to study these matrix coefficients. And so I think mostly I'll work with irreducible Harshadra modules, but Dragan didn't yesterday. He worked for just arbitrary one, or finite length ones or something, for irreducible. So what was a matrix coefficient map? That was a map from, well, if I fix for an irreducible Harshadra module V, if I fix V, then Dragan defined the contragradient. The main point of the contragradient is if you take the linear dual of a direct sum, you get a direct product. So this is not the linear dual, because that would take the direct sum of k types to a direct product of k types. So you had to take the linear dual and then take the k finite vectors. So there's one small subtlety there. But these were linear maps. Here, this is what Dragan defined last time. And what property were these matrix coefficient maps supposed to have? So I'll just recall the notation. Are these any maps? GK equivariant? Just one GK equivariant? Or for what action? Yeah, okay. So this has to be, there's two copies, there's two GK actions, I claim. So there's certainly a GK action here. There's a GK action here. What are the two GK actions here? Left and right. Okay, the Harshadra module of left and right translation on these, on functions on G. Okay, and oh, was there an identity? Oh, I forgot. There's a normalization. CV tilde. Tensor V evaluate at 1 was supposed to be what? Oh, yeah, V tilde V. Or I think the notation was that. Okay, so there's some question about the existence. I mean, this isn't going to be helpful to separate these points in the fiber if these things don't exist. So existence was kind of mentioned. This was attributed, well, for general V, not necessarily irreducible. Dragan mentioned that it's due to Castleman. For irreducible V, it was known earlier to Harshadra. As Dragan reminded me this morning. So we're not so much going to discuss this. Well, we'll discuss this later. But we're going to assume that. For now, in the unicity, Dragan sketched the unicity last time, so let me explain why. Let me just recall what he did, because I'm going to have to recall the equations anyways. So anyway, for this to be a good scheme, of course we would want matrix coefficients of Harshadra modules to be unique, because if we were going to try to tell two Harshadra modules apart, and they had the same matrix coefficients, then this would be a stupid idea. But if they have different matrix coefficients, then we can tell them apart by examining the matrix coefficients. So recall Dragan's treatment of the unicity. Okay, and so this, again, the center comes to the rescue again. The center Z of G, well, I'll write it over here. saves us again because how do, let's say, so now just for simplicity, V is irreducible. Okay, and okay, so I can act by this element of the universal enveloping algebra on this function, right? What is this action? So this is living in the enveloping algebra. How does the enveloping algebra act on smooth functions? What does this dot mean? If I have a function, I have a what if this element, I didn't write some combination of elements in the Lie algebra. I just had it. How does the Lie algebra act? Yeah, so it acts by, say, on the right by left invariant vector fields or something like that. So it acts on the right here by left invariant differential operators. I think if I sorted that out. So this is action. So this is a action by differential operators on functions. Okay, so if it's acting on the right, that translates, because this map is equivariant, it translates into the action on V. V is irreducible, so how does omega act on an irreducible representation? It has to act by scalar, right? So this equals a scalar, okay, and I'm going to adjust the scalar momentarily, times C of V tilde V. So is that clear? That was the main equation that Dragan wrote down, and he wrote it in a slightly different way. He wrote omega minus, okay, so let me call the scalar mu for now. I'm going to change mu momentarily. He wrote the scalar by which omega acts on V times CV tilde V equals 0, and this was the polynomial in the case V was irreducible that he called P of omega. In general, if V is not irreducible, if it doesn't have an infinitesimal character, well, this will be some product of terms like this or something like that. So now I'm going to do a terrible thing, I think. So I'm going to assume V is irreducible, and my assumption is omega acts by, just to make some formulas work out later, lambda plus 1 squared over 4. So if I had been prescient enough, I would have changed my parameterization 2 days ago and shifted every lambda that you saw on Tuesday to lambda minus 1 or lambda plus 1 rather. So this number here, you can cross out the mu and put lambda squared, lambda plus 1 squared over 4. That's just going to make some formulas a little bit nice. Huh?
Why does it have to be positive, the scalar by which omega acts?
No, I mean, this is a complex number. It doesn't have to be.
Oh, okay.
Right, okay. Okay, so the point is, this is a differential equation, right? This is a partial differential equation. And this is acting by a differential operator on functions on a manifold, and we want to analyze it. And Dragan analyzed it. The first point is that we want to understand matrix coefficients. And matrix coefficients, you think of as a big matrix. This matrix coefficients breaks up into blocks according to what? Well, according to how V tilde transforms under K and how V transforms under K. So we're not going to look at all matrix, an arbitrary matrix coefficient. It's enough to look at it understand matrix coefficients block by block. And we're going to concentrate on our attention. So assume, on a particular block, so assume that V tilde lives in, I think this was N, and this was M, but maybe I have it backwards. So that corresponds to looking at a particular, well, in these cases, these are one-dimensional in this irreducible case. So that corresponds to taking a look at a particular entry, okay? And that makes perfect, that's a sensible thing to do. And then we're going to use, then since well, this is what Dragon did last time. Since G is KAK, well, actually, and this A is what, I forget what Bill was calling this A, but I'm going to use Dragon's A, which takes A positive. Okay. So we have this decomposition, and if I know, if I'm fixing V transforming in a known way by this n character of K, and well, V tilde is transforming by the n character, V is transforming by the m character, then this matrix coefficient C V tilde tensor V, which is determined by its restriction to this positive copy of the real line, or this copy of the positive real numbers. And so then the terminology you'll recall is that this is called an Mn spherical matrix coefficient. Well, since this is determined by its restriction to this real line, we should just understand what this differential equation means for this restriction to this to A. Okay, and that's what Dragon worked out by his standard trick or dirty trick or whatever. Yeah.
Since we don't have a group lying around in general, do we build up this group from K and the Lie algebra G, or
Since we don't have a group.
just working with a GK module?
Well, we're not. Okay, so that's
Well,
I mean,
I think your subtitle is misleading because you said unicity, but basically you are not proving anything. I mean, you just write out the equations at the moment for spherical functions, and you are not assuming, so spherical function is a function on a group, and you want to write differential equation for it, so you are not related this to Harish-Chandra module yet.
yeah.
So Harish-Chandra module is, you're right, is something when there is no group, but you can still define certain gadget and study its differential equations, but the connection is not made yet. I mean,
Yeah. So this is a special. I mean, maybe I should have, or what Dragon defined is that this Mn spherical functions were functions on G that transformed under the left by M and transformed under the right by N, something like that. And this is a particular kind of spherical function. And so we should look at the equation satisfied by such spherical functions.
I mean, what you said is a very good point. We don't know that the solution exists yet. Yeah, but it's still a legitimate issue to write down equations assuming that such a solution exists.
Yeah. So this, just to reiterate what Dragon's saying. So we don't actually know that this map C with the indicated properties exists.
So I would add existence and unicity in this subtitle. And in this underlying thing. In the middle board, in the middle board, you said unicity and just assume.
So sorry. That just looked like a bunch of up and downs. I couldn't tell what that was.
Because you attributed to me, I read it carefully.
Okay. Sorry, I'm muddling this up a little bit. So what is this? So the differential equation satisfied by this Mn spherical function is this one. Okay, so I'm just copying down what Dragon wrote down yesterday. So if you think it's magic that a formula like this, well, at least restricted to this A component, can become something as explicit like this, then, I mean, you've seen the magic. Dragon wrote down every magical step in the way. I mean, this is, he showed you how to make, how to make this computation. So what is the quality, this is an equate, okay, so where's this bad at? Where are the singularities in the coefficients at? Well, let's see, if I plug in z is plus or minus 1, I have trouble. And if I plug in z equals 0, I have trouble. Okay? Yeah. Yes. Yeah. Now this is lambda plus 1. Right, sorry. So this should be highlighted. And when you click on it, you should get this. Okay.
What is variable z? I mean,
Oh, okay. So z is in, well, maybe I should, is in this. Yeah. So I'm thinking first of all as
identified
with the positive reals, but shortly I'm going to think of it as a complex number.
So z is the same as a.
Z is the same as a initially, but to solve an equation like this, I'm going to think of it as a complex number. Try to find complex solutions to this. Okay? Which is sitting inside. So this is. So we have trouble at plus or minus 1 and 0, and but the general form this looks like the following equation.
One other question then, if we're identifying A with R positive, why does minus 1 and 0, are they problems?
Zero because
I mean, forget what
I mean,
the interpretation. I mean, just look at this equation in a complex plane.
Okay.
right, so look at this equation in the complex plane. We're going to solutions to this in the complex plane when we restrict them to the positive real axis will give us solutions to the equation we're interested in. Okay, so singularities here. What is this equation? What is the qualitative form of this equation? Well, there's some it's a second order differential equation. The singularities, what am I dividing by here? I'm dividing it by, in the coefficient of f prime, I'm dividing by at most a pole. You know, there's a pole at 1 and a pole at minus 1. And over here, things get worse, but they only get worse by, there's a pole of order 2. These are poles of order 2. This is a pole of order 1. So what this thing looks like, at least qualitatively, is something of the form. So maybe we should change, should call this y or something. Well, I'll call it f still. Right? I mean, I don't have a 1 over z cubed here, or a 1 minus z to the third power here. Okay? I just have simple poles in the coefficient here, coefficient here. So let's examine this. This is called the Euler equation or something. So let's examine that guy. So what's an obvious guess for a solution to this Euler equation? Well, since differentiating twice brings down, reduces the power of a monomial by 2, and differentiating once, but then dividing by z also reduces it by 2, and not differentiating all and dividing by z reduces it by 2. So guess a solution of the form. Okay, so now guess a solution to the Euler equation of the form, well, f of z is z to the r. Right? That's a reasonable thing to do, and then plug it in. And you differentiate twice, you get r minus 1. You differentiate once and you divide by z, you're going to get r, you don't differentiate at all. Actually, let me start putting coefficients here. This is, maybe I should put coefficients to make this a slightly more interesting equation. Okay, so you would like r to satisfy this quadratic equation. I should have. There's an r there, I guess.
And v to the r minus 2. V to the,
And you're the exponent of the
Z to the r minus 2. Sorry, yeah. I think I did that right. Now. Okay, so this is called the indicial equation. So it's a quadratic, it has two solutions. So our general solution of the Euler equation is the linear combination of these two solutions. It's the two-dimensional space gotten by the and that's how you solve the Euler equation, and that's a general solution except when does this two-dimensional space of solutions collapse to a one-dimensional space? When R1 equals R2. So then you've only found a one-dimensional space of solutions, and you have to seek another solution. Okay. So maybe it's better to say, for what we'll say before, except if R1 minus R2 is 0. Okay, so what happens in that case? Well, I don't know. There's this reduction of order which you can use in this case. So you guess a new solution of the form z to the r. So now we're assuming r1 equals r2 equals, okay, so set, so this should go up there, but set r equal to r1 equal to r2. So fix the unique root in this case that we still have to deal with. Guess the solution of the form z to the r u of x, u of z. Okay. Then what happens, you plug this in, you use the fact that you know z to the r is a solution, you cancel, so plug in, use that z to the r as a solution. So then that cancels out a bunch of terms. And you get a first order equation. That's this reduction of order. So you can do this in about 2 or 3 minutes for not for u, but for u prime. So you get a first order equation for u prime, and you deduce u prime. Well, you put in a few more steps here, and just like u of z has to be a log term. Okay, so this already illustrates some of the subtlety of what's going on. I mean, this is away from the singularity at 0. So how do you interpret log? Well, it's probably best to think of log as a function on the cover of the punctured disk. Let's not worry so much about these multi-valued issues, but just the form of the solution. So in this case, in the R1 minus R2 equals 0 case, the solution is, general solution is, well, f of z is, well, you've got z to the r in both places, but then you've got this extra log term. Okay.
Can I just
Sure.
make a comment to
Sure.
answer to his question, actually?
Yeah. Okay.
So you ask what is the difference between real and complex solutions.
And of course, this illustrates what's going on. If you study the general equation of this type, I mean, coefficients are holomorphic, so around any point, the space of solutions is two-dimensional. If you look at the equation on the real line, the space is solution is also two-dimensional. So this means that any real solution is a restriction of a solution in some neighborhood in complex plane. And this is basically what you use to study solutions, to study the solutions in a complex plane. And in this way, you see that locally your solutions, if you avoid, say, regular singularities around regular points, is a restriction of holomorphic function. So it's given by Taylor series, so it's real analytic. And this is what actually I was using in the proof of uniqueness to know that matrix coefficients are real analytic functions. Does this answer your question?
Yeah.
Okay.
Yeah, so certainly I was going to remark on that the solutions of this equation for tau spherical functions, well, we've just talked about the Euler equation. We'll have to come back to talk about the equation that we have at hand. But it's exactly as Dragan says, this proves that any solution of this is real analytic. So if we had a matrix coefficient map, that would mean, assuming the existence, that would mean the matrix coefficient map landed in real analytic functions. And that's exactly what Dragan needed to conclude unicity of the matrix coefficient map, right? Because in the neighborhood of the identity, the matrix coefficient map is determined by the Harish-Chandra module structure, just by exponentiating. And then once you have this real analytic fact, you get it everywhere on G. Okay, so that's important. So now we're going to translate this qualitative behavior of this a simple version of this equation to get the qualitative behavior of this. Okay? So what's the difference between this equation and this equation? Well, the singularities have the same, as I remarked, well, this we're studying, this is singular at 0, only at 0. So let's just concentrate at the singularities at 0 here. Okay, so we're going to study, we're going to get power series solutions in a neighborhood of 0. Not in some neighborhood that doesn't contain plus or minus 1, so say the open disk, the punctured open disk. So let's rewrite this as, well, f double prime of z plus, well, 1 over z, and then I can just expand this thing in some power series that what's the first term of this power series, since I have 1 over z, it's going to be z squared plus higher terms times f prime. So I'm just expanding these coefficients in a neighborhood of 0. And this next term, I'm pulling out a 1 over z or 1 over z squared when appropriate and then expanding. And this, let's see, so I'm going to get the first term that this is going to start with is this magic lambda plus 1 squared over 4 plus higher terms. Right? If I pull a 1 over z squared out of this guy, then this series is going to start with z squared. If I pull a 1 over z squared out of this guy, the power series expansion is going to start with z. If I pull a 1 over z squared out of this guy, it's going to start with this magic constant, lambda plus 1 squared over 4. And this is supposed to, times f is supposed to be 0. So if we erase the higher terms, we'd be, oops, what? Oh, yeah. So already, maybe this counts as a higher term already. If we erase,
why does it start with z squared? Shouldn't there be a constant term in the bracket 1 over z times?
well, let's see. We expand this about 0.
Yes.
And so if I have a 1 over z squared, then the first term in this is going to be, oh, maybe you're right.
I think.
Oh, no, I don't want to pull.
I think you
What did I do wrong here?
This is not the equation I calculated. I think that term there is something wrong in it. So
Wait.
you're right. I mean, put a question mark there. This
Wait.
really is. Yes.
I mean,
Wait, I don't understand. What's my problem? You don't like?
I don't think that this is the correct
What-
formula,
what-
but
so
Oh,
so
okay,
you had
I-
ZD, you had ZDs, you wrote it as something like ZDZ squared plus,
Minus 1 plus z squared over 1 minus z squared. Z dz. Z d by dt.
yeah, I mean, you were writing in these,
It's 1 minus z squared over 1 plus z squared. 1 plus, I'm sorry. 1 plus minus 1 over 1 plus.
yeah,
so you're claiming I make an
I
algebra?
mean, I don't know. It looks unfamiliar to me, but I mean, definitely this in a Euler equation, I think this middle term has to disappear.
It does disappear, right?
Yeah.
Because you look, I mean, the constant term is 0.
Yes.
So my initial equation is going to be okay. I mean, maybe I should write this as 1 over z plus 0 plus higher terms, if you want. I mean, the first term that appears in this higher terms is z squared. Don't you agree?
Yeah.
Isn't that what I wrote?
Well, you divide by g squared. I mean, the term of f double prime is 1. In your equation, the coefficient of f double prime is 1. So
Yes.
you divide it by g squared.
Yeah. Yeah, I
So g should be in the denominator.
On 0.
Huh?
So that g that appears in the numerator
should be in the denominator. Is that what you're saying?
Otherwise, there's no one over z term at all.
But that's I think that's I don't think there is a. I think this is 0. I think this disappears. Isn't this is 0?
It has to disappear.
Yeah.
This is my main objection. I mean, this, the real form of differential equation is irrelevant. What's important is this.
Is what-
you don't pay attention
To this, but
detail.
this is correct. I mean, no,
You don't really want to solve the equation.
no, I don't really want to solve the equation. I'm not going to solve the, but I'm still standing by this.
Something like that.
I still stand by this. So.
I think you have 1 there instead of.
No, I definitely don't have 1 here. That's the only thing I'm sure about. The only thing I'm sure about is there's 0 here. Well, I'm sure of that too, by the way. I mean, I'm sure of all of it. So this is a 0. Yeah, because Matvey, there's a z dz everywhere. So when I divide by z squared, I'm getting. Well, anyway, we'll sort this out later. Huh? Let's just concentrate on this over here. Okay.
Okay, shift equation. So if lambda is negative 1, so then on the other, like in the last term, you would have 0 from higher order term.
Yeah.
Would that be a problem?
No, there's no problem. I mean, it's possible that the scalar by which the Casimir act is 0. In fact, that's the example that Bill was talking about, right? Because the Laplacian, he was looking at harmonic functions. So then the Laplacian is on G mod K corresponds to how the Casimir descends to G mod K. So, and he was looking at harmonic functions. So indeed, the Casimir acted by 0 on those functions. So that's okay if this is 0. Okay, so how are we going? What did we guess before? Well, if I erase these higher terms, I've got the Euler equation, and so the solution I should guess is f of z is, we said z to the r, but then I've got to patch it up by higher terms, right? Those higher terms. Okay. And so then I write down that what's the corresponding indicial equation. Well, that's where I just ignore the higher terms. I want an equation on r, so I erase those. And I get, I think, r times r minus 1 plus lambda plus 1 squared over 4, okay, equals 0. So now the reason for the shift by lambda 1 probably is becoming apparent. So let's see. So this is r squared minus r plus lambda plus 1 over 2 squared equals 0. And I think we apply the quadratic formula, and you get r is 1/2 plus or minus lambda over 2. Okay, so that gives us the leading term of our guessed solution. So now we plug in this leading term, go back to the original equation, and just write it down and figure out what these higher terms have to be in terms of these higher terms. You can imagine, I mean, I'm just writing this as a series, z to the r plus k greater than r, I don't know, b, k, z to the k. I plug that in. I know my leading term is going to match up appropriately. That's what this calculation did. And then I just have to get some sort of recursion relations on what bk is going to be from what these guys are. So. Okay, so negative b, so it's plus 1 plus or minus b squared, 1 minus
Lambda plus 1 whole square.
4ac plus 1 squared. Okay, why does that look bad? Okay, so and this is over 2. Did I really want I? That doesn't seem right. Oh, I know what I did. When I bring lambda, this should really be a minus here, because that was my only mistake. Because remember, this operator is supposed to act by this scalar. So this times f is supposed to be, maybe I should write it.
But even then,
Maybe I should write it like this. This times f of z is lambda plus 1 squared over 4 times f of z.
yeah,
Huh?
the thing under the square root will still not be a square.
What a mess. Okay, so I even screwed that up. So let's just make. Oh well. I thought this was going to fix that.
And in the right hand side,
Anyway, so let's just it's just plus or minus mu, whatever mu is. So
I think in the right hand side is there a 4z squared in the denominator? Is there z squared in the,
over here,
yes.
no, this is just a scalar. I mean, this operator acts by scalar.
In the previous thing there was a z squared, the denominator, 4z squared.
Well, yeah, yeah, you're right, because I should divide it by z squared. Yeah, something like that. Anyway, please don't worry too much about these details. That's not important. So the important thing is that our guess solutions look like well the general solution looks like some constant times. Try to get this row shift right, but this is all screwed up. So anyway, I'll write it like this. So a z to the mu times some power series in z. So really some power series, no negative powers here, in positive powers of z. Plus b z to the minus mu in power series in positive powers of z. And we're getting these two power series by these recursion relations. And again, there's a fly in the ointment, except if, well, we certainly have a problem if mu equals 0. That is, if r1 minus r2 is 0. Well, yeah, if r1 minus, if we get a collapsing. But we also have a problem, it turns out, when you study these recursion relations, these two solutions will collapse, or you'll get stuck somewhere. You'll get stuck if 1/2 plus mu minus 1/2 minus mu is an integer. So i.e., if 2 mu is an integer, and if I were careful and I kept track of what mu was, if and only if lambda from 2 days ago, or lambda plus 1 from 2 days ago, the scalar by which, no, let's see. Yeah, well, anyway, if this is easy. Yeah. I think that's right. Does that sound right, Dragon?
I mean, again,
It doesn't matter?
to stress that you are just proving a very important principle that one should never really care about details of the
I don't care. I don't care about the
calculations,
details of the
because
calculation.
at the end, the answer will be obvious.
Yes.
You want to use differential equations to just get the pattern of solutions.
Yeah.
Then everything in there will be determined by other data.
I guess that's right.
You get from general theory that the solution will be analytic, so you can use the power theory.
Yeah.
Yeah, that's the whole point of this only being a 1 over z here and a 1 over z squared there. I mean, if there were 1 over z cubed here, you'd be in trouble.
But in the next lecture, you will see what these leading exponents actually are in terms of algebraic data.
Right.
Chandra modules, so it will be clear what is the right number.
Yeah, so
Solving quadratic equation actually is not very.
not very important, but and there's this point that Rishi is mentioning that these formal recursion relations give me a power series. How do I know that this power series converges? And that's guaranteed by the form of this equation, that there's only a 1 over z here and a 1 over z squared. If you had a 1 over z squared here, for instance, you'd do this formal process, you'd get something that formally is a solution but doesn't converge, or something like that.
Question.
Okay.
Why does the second situation present a problem?
I didn't actually check why, but I think the reason why is that when you go through these recursion relations, when you try to solve, you can solve, you get stuck for one of them, but not the other one, or something like that. So if you actually try to compute a formal solution, does that sound right, Dragon?
I mean, there is only one formal power series solution. I mean, again, the whole thing is very naive. This is what I mentioned as answer to this question. What is the theorem? The theorem is that if you have a system of, say, differential equations with regular singularities, you can consider formal solutions, formal power series times certain powers of log, and you can formally differentiate that. And then you count dimension of space of solution, and that number is the right one, is the order of your differential equation. So this says that every formal solution is convergent. This is the big theorem, what Peter is using implicitly. So you solve recursion relations and you get some formal power series which converges just by abstract nonsense.
Yeah, so let me mention what the solution is in this cases. So just like in these cases, sorry, you have a question?
Was this question about the second one, why that should be?
Yeah, so
Well, if the second one is true, then one of those two up there collapses into the other.
Okay, so Curtis has checked this. So, or he's done this enough to know that what happens is if you try with one exponent, you get the same answer as if you do it with the other exponent. So you get this you do this recursion relation, and the span of these two is one-dimensional. So what happens, so as Dragan says, you have to consider more general formal power series solutions. Those are suggested by what happened in the Euler equation. And the more general power series solution that you get in these two cases are, well, you have the z to the mu to the 1/2 is now sitting out in front, and then you have a plus b times some log term. So that's just exactly what happened. Well, we didn't quite see this in the Euler equation case, but certainly when we saw that the two roots of the initial equation collapsed, we had this log term. So as Dragan was saying, you have to consider more general formal solutions in general, and these are these log formal solutions. Okay? So maybe I should just summarize all these marvelous calculations. So maybe I'll summarize it in a way that makes sense that makes sense in general. Okay, so here's the theorem. So this is called the Harshchandra expansion. Okay. So let f be a spherical function of type m n. So what would you do for general GK modules? Well, it would just be of type mu nu or something. You would look at one that transformed on the left by mu, this k-type, and on the right by another k-type. Of a Harshchandra module. And just because I was making life a little easier with infinitesimal character, chi. So that just means in the SL2 case, i.e. omega acts, so this is a Harshchandra module V, omega acts on V by a scalar. Okay, so you could take a sum of two irreducible representations, for instance, where it's acting by the same scalar, if you wish. Okay, so then there's a set of complex numbers, S chi, so that only depend on chi, it doesn't depend on V. Okay, so no two of which differ by an integer. Okay, so in this SL2 case, we'll let S chi be, well, the roots of this initial equation, 1/2 plus or minus mu. So, well, it's either 1/2 plus or minus mu, or one of them if they differ by an integer. You see, this was the first case we considered. If they differ by an integer, this S chi just has one element. Okay, and a subset. Oh no, actually, this set will be just that. No, if they don't, okay, or 1/2 plus mu. And a subset SV that depends on the Harshchandra module, okay, such that, and these power series FSM, okay, so this is S in this S chi, M in Z, such that, well, this spherical function has this expansion. This is the formal power series part. Let's see, maybe I'll go back to the variable A or something, A to the S, and then there's some log terms appearing. So this is on A minus, which is equal to the set 0 or A 0 0 A inverse, where A is between.
Yeah, you should either have alpha or A.
Okay.
Your notation is inconsistent.
No. So sorry, this should be different. Okay. Okay, so, and this expansion is, yeah, so where is this a sum over? This is S in SV. That's what depends on the Harshchandra module. And yeah, so, okay, I guess maybe I just have to take these positive or something, so. Yeah, of course, greater than equal to 0. Okay, so that's the general form that we kind of deduced from this, considering the Euler equation. We had some powers of mu times, some powers of z, which would restrict to the real line, becomes this parameter, this variable a. We had those. We also had to consider log terms in general, and the log terms came about when we were in the special case where these leading exponents, these so-called exponents, collapse. They differed by an integer. Okay, so this is the general expansion, and as Dragan was talking about, this SV, the set SV. So preview of coming attractions. The set SV can be characterized algebraically. So even though these kind of leading terms in this expansion, is a to the s. I mean, these are the biggest exponents up here because you're multiplying by power series that have all terms in a that are higher powers. Those leading terms in this expansion can be characterized purely algebraically, and so in terms of homology, certain kind of n homology. So this is an idea of Castleman's, and that was expanded on by Castleman and Milicic. So what I had hoped to do, I mean, my time is definitely up, but what I had hoped to do was also analyze the indicial equation around the singularity 1. And then you get some interesting, that equation. See, it's interesting to note that these x, m and n never appeared in this indicial equation. But around 1, m and n appear, and there's a lot of fine information about the singularities at 1. So understanding when they're regular, how they're regular, gives you more detailed information about the Harshadra module. But I didn't get that far. So what you're supposed to take away from this is that the general form of a tau spherical function has this expansion, and this is really the key. This works perfectly generally. We saw how that expansion came about just very explicitly from the simple so-called method of Frobenius. There's these, what emerges are these so-called leading exponents, which are these numbers in this case, and that those leading exponents will play a role even in the algebraic theory. Or, I mean, they're really a central object because they appear not only in this analysis of matrix coefficients, but they'll show up in the algebraic theory too. So, question?
What is the role of S chi? You did not use it anymore.
Well, the point is that all of these SVs, I mean, there's some uniform set that they're all drawn from.
It's determined by their infinitesimal character.
Yeah, it's kind of a stupid. If you knew going in that there were only a finite number of Harshadra modules with the irreducible Harshadra modules with a given infinitesimal character, then this may not be so interesting with the way I stated it. You could say this anyway. I'm just going to leave it like that. You can't get. There's just all these leading exponents are drawn from a finite set once you fix the infinitesimal character. So.
Wait, S chi is finite? We don't know that operator.
I know it is. I should have said finite here.
And the range for k is also finite, isn't it?
Yes.
The range for k is finite. Yeah, so I should have said that. Only.
Yeah, this is a finite sum.
This sum is finite. Yeah. Finite sum. That's a very important point as well. You can see why. I mean, the dimension of the space of solutions is bounded by the order of the differential equation. So. Okay, it's a good place to stop. So Milicic comes on next, and then we're done for today. So we'll take a break till 10 o'clock.